I heard the bell. I'm so excited. We have show and tell and more show and tell today. So that's and I'm very thankful that you're here. We're grateful for the visitors. Always love to have visitors, and I pray that we make you feel welcome. And we're gonna have a prayer in just a moment. But Tyler showed me how to get this to run on YouTube, where we could see it on big screen. Now the only speakers are going to be the computer speakers, so the sound will be a little soft. We'll have to listen carefully to the sound. But I have to tell y'all that this is one of the most imaginative videos you will ever see. It was made a long time ago. You can see in 1977 by a husband and wife team. This video was made for IBM employees. Hi, y'all, come on in. It's made for IBM employees. And what they were trying to do is to help the employees understand something about the scale of distance and numbers. Try to get their mind wrapped around the scale of distance and numbers. We have a hard time conceptualizing big numbers, don't we? Like if I say 1 in 10 to the 16th power, you have no idea what that means. I mean, it's a lot of zeros, but you know, what exactly does that mean? So this husband and wife team made this video for IBM employees to try to help them understand something about the scale of tremendous distances and numbers. And I showed this to Robin first time. I said, "What do you think?" She said, "Show it again." And then she said, when she watched it the same time, "You better explain it before you show it." Okay, so that's what I'm going to do here in just a minute. Before we begin, we're going to approach our Heavenly Father and ask Him to bless us in our study. David, would you word of prayer for us, please, sir?
Father, thank you so much for letting us be here, and thank you for letting those of us who've been sick feel better. And Father, thank you for the ability to meet freely, to study your word. And Father, thank you for all the times we encounter people that are not of the following of Christ, that we can help win their souls and minds over to you. And we're grateful, Father, above all things, for Jesus, our Savior, that He gave His life for us, that He reigns with you now in heaven. Father, we pray as we go through this study, we pay attention and apply the things we learn today to our lives. In Christ's name we pray, amen.
Amen. Now these two boards, because I wasn't sure if we'd be able to get this to work today, they will probably be up here next week as well. I don't think we'll be able to get to this. But the great verse in the Bible, if you stop and think about it, I mean, is the very first verse. In the beginning, God created. In the beginning. And a person either accepts that or doesn't accept that. In the beginning, God created. But have you ever thought about just how magnificent creation is, and about how big creation is, and then how small creation is? And so what this husband and wife team did, I got to kind of explain it because it goes quickly. It's only 9 minutes long, and it takes a little while to wrap your brain around it. Is it starts with a couple in a park, and the screenshot is a meter away from the couple in the park. So it's above the couple in the park at 1 meter. And then every 10 seconds, it goes back a power of 10. All right? So it starts out at 1 meter, and then 10 seconds later, you'll see a square, and that square is at 10 meters. And then 10 seconds later, it's at 100 meters. And then 10 seconds later, it's at 1,000 meters. And then 10 seconds later, it's at 10,000 meters. And it just keeps going until you get to the edge of the known universe in 1977. So it goes back all the way as far as you can at the universe that they knew at that time. All right? Really. And then it collapses back down. Real quickly, it'll go back down to that couple in the park, and it'll start going the other direction. It'll go 10 to the negative first, into the hand, and then it'll keep going. And another way to think about this, it took me a while to wrap my brain around it, is every time it moves, it's covering 90% of the remaining distance to as far as you could go, as they knew, to subatomic particles in 1977. All right? So it takes a while to get this conceptualized. And here is the important thing for you to remember. You know, we talk about these big numbers. The entire distance from subatomic particles to as far as they knew of the universe in 1977 is 10 to the 40th power. Okay? All right? So that's important. So this number is so big, well, this is how big it is. Okay? All right? So may I show this to y'all? See what you're saying? Yeah, move around or whatever, however you need to move around and I was hoping for more than that. All right. Quit doing that. I got you. Shall we turn off lights? Yeah, maybe hit the light back there. Looks very 70s, doesn't it?
The picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October.
Oh, that speaker is through the
We
TV.
begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is a kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds. The day's weather in the Middle West. 10 to the 6th. A 1 with 6 zeros. 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey.
That's 10 to the 7th meter.
Earth diminishes into the distance as those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the sun. Followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth.
Look, we're just at 10 to the 15th.
This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy.
In the beginning, God created. Look at that.
Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home.
And that's only 10
This
to
lonely
24.
scene, the galaxies like dust, is what most of space looks like. emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we will be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary, containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus. So massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks in intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
That's it. Now y'all see why Robin said, show that again. So the next time you read Genesis 1:1, in the beginning God created the heavens and the earth, I don't think I'll ever read that verse the same as I did after that. You can go to YouTube and just type in Powers of 10 and that will come up for you. Or you can buy a DVD of it as well. But anyway, I thought that was pretty neat and tells us something about the creative, if you're a Bible believer, something about the creative power of God. And then it helps me appreciate the scale of numbers a little more. If that's 10 to the 40th, all the way from the nucleus of the atom to as far as they knew the universe extended, that's 10 to the 40th. That tells you something about the scale of numbers too, doesn't it? Yeah. Any other thoughts or comments on that? That's kind of way cool, isn't it? All right, how do I exit out of all of this? Do I care? There you go. Everybody needs to have a tech person. Okay, there you go. Good deal. All right. Now, one thing I want y'all to be thinking about today, the other verse I want you to be thinking about is the first verse up there, Genesis 1 and verse 24. Then God said, let the earth bring forth the living creature according to its kind, cattle and creeping thing and beast of the earth, each according to its kind. And it was so. Things reproduce after their kind. And so, cats give birth to kittens, dogs give birth to puppies, and so forth. And I think we all understand that. But I want to start delving into that just a little bit more, if I may. And we're going to have some show and tell this morning, and it's going to require a field trip, okay? So we have to go out to the portico out here. And Frank, would you bring the bicycle, because I want you to be seen with the bicycle, not me. And bring the bicycle with you out here, and I want to see if I can show you all a couple of thought experiments.
Do you want it recorded?
Yes, that's fine. You can record it, Barrett, absolutely. And you don't have to bring anything. Jacket, yes. Actually feels pretty good. And Frank, if you wouldn't mind, go stand next to the motorcycle. Don't you remember how excited you were in school?
Oh, yeah.
Yeah, no, go ahead, stand in. There's no line.
You're gonna be so.
Good job, Frank.
Hello there.
Yeah, that's right.
Anybody
I almost caught myself saying 7 pounds. One of the points that I tried to make to y'all at the beginning of class is that I know in the popular literature, like if you're listening on the radio or TV or online or reading a magazine at HEBs, that Darwinian evolution is still talked about a lot. It's still a very common theory. It still is a common theory. However, in the peer-reviewed literature, I'm talking about the scientific journals, more and more questions are being raised about Darwinian evolution because scientists are realizing that it really doesn't work. And I'm going to try to show you this morning the main reason why it doesn't work. And this is a thought experiment, and the questions may seem obvious, but I really want you to think about it. Now, I think everybody here would agree with me that the totality of this bicycle is right here. Everything that makes this bicycle a bicycle, its genetic blueprint, if you will, is right here in front of us. How do you know that that bicycle was designed? Everybody knows there's a builder, there was a manufacturer somewhere, somebody put that together, but how do you know that? How do you know just by looking at it?
It works.
Okay, now explain that. Now, Julie, that is a good beginning. She said it works.
It functions
Okay.
properly.
Oh boy, you're A+. Give her a sticker. All right, that's exactly right.
It doesn't
It
need
has
anything else.
functional design parts that accomplish something. All right, and I think we immediately recognize that. I mean, that's just common sense. You look at something and you say it's got a lot of parts, and we know how it functions. If I turn the pedal, the wheel turns, the chain is attached, and we can see that it works. It makes noise, that kind of thing. So we can see that, can't we? Now let me ask you something. if I started messing with the totality of that bicycle there, are there parts I could change or take off and it would still function as a bicycle? Okay, now Robin, what could I take off and still have it function? Okay, so I could take off the bell and it would still function. I could take off the pretty ribbons, and oh yeah, and it would still, yes, I could take off this little backpack thing here at the beginning and it would still function as a bicycle. But would I, if I kept taking off parts, would I run into problems before very long? All right, because there are some parts that you can't take off and still have it functioning. All right, now leave the bicycle for a moment, and I want y'all to think about Lynn Angel's motorcycle here. And again, just think about this as the totality of this motorcycle and be comparing it to the bicycle. They're both modes of transportation. They'll get you from point A to point B, but in radically different ways. But again, when you look at that, do you know that it was built or designed by somebody? And do you know that it was designed or built for the same reason that you know this was designed or built? Why? They're functional parts. They work together. They have specific tasks that they accomplish. They're made in a particular way. It's very complex. There's a complexity there. And there's more engineering in it than you might imagine. You know, if you had to try to figure that out for yourself, it would take a long time. Now here comes the second part of the, and by the way, could we take some parts off this motorcycle and still have it function as a motorcycle? Some parts, yes. Lynn, what could we take off and still have it work all right? Okay, you could take off the windshield. It'd be cold today, but you can take it off. That's right. Mirrors. What else? Sound bags. Yes. So there. But would you run into problems before very long if you started taking off parts, or would it function less well? Let me say it that way. Would it begin to affect the functioning almost immediately? It would begin to affect the functionality and the usability. Now here comes the key question this morning. If I got a really smart person, the smartest person you've ever met, and I had him take the totality of this bicycle right here and change it into that motorcycle without going out and getting other parts or something like that, but I just stuck with the genetic blueprint of this bicycle here, could even a really smart person turn that bicycle into that motorcycle? No, nobody, but why? Why could you not do that?
Don't have the parts.
And now say it again.
Don't have the parts.
Okay, so what are some parts that you don't have in the bicycle that you have to have the motorcycle? Okay, gas, engine, electrical parts, all right? You know, immediately you can see that. There are whole systems in the motorcycle that are not here in the bicycle, right? So there's nothing here in the bicycle that would fit the gasoline over there, or the electrical parts, or anything like
And
that.
we just thought, yeah, and the, you need to stop it too. So
Oh, brakes are different. You know, clutch, everything is different. So there is completely new information and new parts in the motorcycle that are not in the bicycle. Now what if? And now this we're really starting to multiply the problems here. What if you didn't know that you were trying to change the bicycle into the motorcycle? Would you be able to change it into the motorcycle? No. Now, friends, by definition, evolution is a random, undirected process. That's the definition. It is a random, undirected process. It doesn't know that it's trying to change the bicycle into the motorcycle, right? So even we know you couldn't do it even if you were trying, but you're sure not going to do it if you're not trying or you're not aiming for that. I think everybody sees that. All right, now I want y'all to apply that to biological evolution. You start out with the bacteria. Here it is. Here's the sum total of the bacteria. And over here is John Evans, the human. All right? Can the bacteria change, even if you give it 60 zillion years, change into John Evans? Why not? Yeah, just think of it. There are whole systems that I have. There are whole parts that I have. There are complexities and functions that I have, just like the motorcycle, that the bicycle doesn't have at all. And evolution does not account for new information. Now, can it account for natural selection? Like, can I change the bicycle a little bit within the, and can I take parts off and that sort of thing so that it'll work? Yes, I can do that. But I can't give it all new information and new systems and new parts and new complexities. Now, we're not the first ones to figure that out. Scientists have been looking at that, and they realize that there is not enough information. There are not the parts, there's not the function there to allow us to change into something more complex. And because of that, then doubts about Darwinian evolution are beginning to creep in even to the scientific journals, the peer-reviewed journals. And so they're trying to figure out some different kind of evolution that will work. But just be thinking about it. If you're talking to somebody, just be thinking about this really simple illustration. And I think we know that can't become that. But you're thinking the bacteria can become this if I give it enough time. Doesn't matter how much time you give it. There are parts, there's systems, there's tissue, there's complexities, there's functions here that there is not that information in the one cell bacteria. Lynn?
John, all the evidence says if I don't take care of that motorcycle, that bicycle doesn't go.
Yes, yeah, devolves. That's right, yeah, that's right. Okay, any questions or comments about that? Y'all are good to put up with this, but I really appreciate it. Okay, let's head on back in. Oh, thank you very much. I mean, it sticks in your mind. Yeah, that's right.
I've had worse jobs.
It's not exactly.
How are you? I don't put my jacket
Yes, that's right. Now, I want y'all to be thinking about something, if you would, for just a little bit. So, when you start messing with our genetic code, usually bad things happen. Now, occasionally something happens that may seem like it's an advantage, that it's good, but just realize that usually when the genetic code is messed with, it's not a good thing. Think about conditions like Down syndrome, for example, various birth defects, that kind of thing. Usually it's not a good thing. I know Amber was telling me about one particular with her mother and her cancer. Can you tell us about that mutation?
So my mother has had breast cancer 3 times, and they finally did a genetic test to find out that she has a CHEK2 mutation, which is a genetic mutation that does not allow your body to catch cancer. And because your body catches cancer like it catches viruses and bacteria and attacks it with the immune system.
And so she doesn't have the ability to so that makes it more likely she would develop the cancer.
Right. So there are certain cancers that her body doesn't catch and get rid of.
Catch it and prevent it.
Right.
Yeah.
So that's an example of a mutation that's not useful or helpful.
Yes, and any geneticist will tell you that 999 out of 1,000 mutations are automatically bad for you. A good one is a very rare thing. Almost always a genetic mutation is going to cost you something. for example, what you just said. So the scientists are seeing what we saw out there. They're recognizing that, and that's caused them to raise more questions about Darwinian evolution. And so then that causes them to try to find other forms of evolution that they think will work, will allow the bicycle to become the motorcycle. And so, for example, let's move over to this side of the board if we may. I want to talk to you for a moment about a name we've mentioned before, Lynn Margulis. She died in 2009 or 10, so she's been dead for over a decade. But she's a name that you will see over and over again. And she developed a different theory of evolution. She was an endosymbiotic evolutionist. Endosymbiotic evolutionist. And I heard that on the radio for the first time the other day, endosymbiotic, right? And her thought was, well, here's how you get a more complex system. She says, for example, y'all remember when we studied cells in high school, the mitochondria were the powerhouse of the cells. She said that the mitochondria started out as bacteria over here, and so it was independent bacteria, and then it formed a symbiotic relationship with other things and came over here. So she said they started grouping together. These simple things started grouping together and forming a symbiotic relationship. In plant cells, she would say the chloroplasts were originally independent structures, and then it formed a symbiotic relationship, and that's how you came up with evolution. Right now, do you see a problem with that theory, by the way, too? You know, it doesn't answer the question, it just moves the question to a different place. So my question is, and where did the mitochondria, or where did the bacteria come from? You know, it doesn't really answer the ultimate question of where life came from. It just moves the question to a different spot. But I want to show you, so she is an evolutionist. She would not agree with us on almost anything, right? But here's what she said, and by the way, she was identified as one of the 50 most influential women in science. One of the 50, so heavy hitter, somebody with a lot of reputation. She would stand up before a group of microbiologists, evolutionist microbiologists, at a scientific conference. So she's standing before folks who all agree with evolution, and she would just ask them to name a single, unambiguous, clear example of the formation of a new species by the accumulation of mutations. She said, just give me one example of a new species by the accumulation of genetic mutations. And she's saying that to people who do it for a living, that is their specialty, and they believe that it happens. She said, well, just give me one example. And guess what happens? None. There ought to be thousands. I mean, there ought to be, the examples should be everywhere if it happens. So she is a very provocative person. She had a lot of weird ideas, but that's a really confrontational thing to ask in front of a group of scientists. But the point she was making is, you can't show me the motorcycle from the bicycle. You can't show me the new species. Yes, Greg?
You had indicated that mutations like 99%.
Yeah, the overwhelming majority.
Is there an example of any beneficial mutation?
Yeah, there are some that give certain benefits, but usually it's at the expense of something else. So for example, think about the different colors of bears. So white color of bears, polar bears, for example, does that help in the snow? Right? Okay, so that would be that they theorize that was a genetic mutation, just the color of the skin.
But it's not necessarily a mutation.
May I give you another one? And this one is going to be harder, and I'm going to make sure that I word this in the right way if I can. Should you do this, John? Yeah. There we go. Pass that through my filter here, okay? So here is a particular mutation that affects folks of color, all right? Folks of color, most of you know, can be afflicted with sickle cell anemia. Everybody heard that, everybody knows about that, right? And that seems to affect people of color more than any other group, all right? Now, why is that? Why is it just in black folks? Right? Do you know? Because of genetic mutation. And you say, well, Greg's saying, John, that's not helpful to have sickle cell anemia. Did you know something that the sickle cell anemia mutation does help you with? There, doctor said it. People who have, if you just have the trait but not the disease. If you just have one parent with the sickle cell anemia, then you don't get malaria. And where people of color, where's their home? Start from, right? So would it help to have the sickle cell trait, not the disease? If just one parent gives it to you, you don't get the disease. Would it help to have that if you lived in a warm climate where malaria is common? Answer is yes, it would. Do you want to have the sickle cell mutation? Anybody here want to have that? Because if both parents have it, then you get sickle cell, right? So it does help a little bit under certain circumstances, but the trade-off is you could end up with the sickle cell disease when you kill it, right? So it protects against malaria, but it makes you vulnerable to the sickle cell, right? That's kind of interesting, and if you're like I am, I have to kind of think through that. But it's kind of interesting, and that Greg shows you one that is potentially helpful in one way, but do you see the price that you pay in the other way? And almost always that's the way it is. There's some trade-off. Yes, Jamie?
I think I brought this up the first class. I've never even heard the question asked, how in almost every species does the male and female develop together when the systems are completely different?
So you take the anatomical differences, chromosomal differences between male and female. How would you get that if we're all coming from one common ancestor? That's a really good question to ask. I think that's a good question to have in mind. Now Lynn Margulis that we were talking about, here's the second thing she says. She said, history, and again, you can see how provocative she is. She says, history will ultimately judge neo-Darwinism as a minor 20th century religious sect. You imagine this makes her real popular with other scientists. Within the sprawling religious persuasion of Anglo-Saxon biology. Think through that. She said, I think we're going to realize that Darwinism, it doesn't work, it can't work. And then we're going to find out that we have to go somewhere different. Of course, she's trying to push what? She's trying to push her idea, right? And the point she's making is neo-Darwinism. Now remember, Darwin talked about natural selection. Neo-Darwinists add genetic mutations, genetic variations of that. Does not give you new kinds of organisms with new genetic information. Doesn't give you new organisms with new genetic information. Does natural selection allow you to have improvements within a species? Can you get improvement? Can animal breeders breed for a particular trait? Yes, they can do that. Finches, if they have longer beaks, can they get seeds that other finches can't get? Yes, that happens. That microevolution within a species does happen. But it doesn't give you totally new organisms with new genetic information. And remember, she would ask that to a group of scientists, and the scientists were not able to answer that. Because it's really pretty provocative. Something to think about. Anybody have a question or comment? You know, I was thinking, Dustin, about like boar goats. Can you breed for more of a Roman nose in boar goats and get a particular color and that sort of thing? But the boar goat never becomes a different kind of goat, does it? It doesn't become a new animal. It doesn't change into a new animal. And Lynn, I was thinking about, you know a lot more about plant breeding and that sort of thing. Can you improve varieties of pecans and so forth? But the pecan never becomes a pear tree, does it? All right? Why? Because it doesn't give you new genetic information, just like the bicycle cannot change into a motorcycle. You have whole new systems, whole new functionalities there. All right? Yes, ma'am?
John, I was thinking, I'm gonna go to my motorcycle. I can identify all those parts. So someone can, right?
Yeah.
That doesn't put the motorcycle together.
That is
And a lot
exactly
of the
right.
scientists, if you think about it, they've identified the parts, but it stops there for the most part.
I'm gonna see if I could write this name up here just so y'all can have it in front of you. You'll read in the evolutionary material, the most famous experiment is the Miller, let me turn on my spell checker here, Miller-Urey experiment, where they heated up some chemicals in a flask, zapped it with some electricity, and they got some amino acids. And they said, look, we've made life. And No, you've made amino acids. You don't have them in the right order. You don't have the right bonds between them. You don't have them organized into protein molecules. Yes, if you put those chemicals together, you'll get amino acids. That's what the amino acid is made out of. But you haven't made life. Yeah, not even close to it. Right? Anybody else have a thought or comment there? Oh, this is good. I'm enjoying this. All right. So, when we were in school, we were taught the scientific method, right? Everybody was taught the scientific method. And what did your science teacher tell you? You come up with a hypothesis, a possible explanation. You test it, you see whether or not it works, and you can repeat it. Anybody who repeats the test should be able to come up with the same result. And we were all taught the scientific method. But friends, realize that the scientific method does not work for everything. Because there are some things you can't retest. Can we go back and retest how life began? You can't retest that, all right? There are things that you cannot retest. So what you have to do is you have to use the inference to the best explanation. In other words, you consider all of the information. You consider all of the evidence. You consider the kinds of things that would explain what you're seeing, and you put that together and come up with the best explanation. What's the most logical way to explain what I'm seeing, all right? When you look at the bicycle, can I deduce that there is a designer somewhere, that somebody manufactured that? I absolutely can. Okay, look, right here, all right? 37 trillion cells in the human body. 42 million protein molecules in each cell. We won't get to the bottom part of this yet, but does that sound like there's a designer somewhere? Or a random, undirected process cause that to happen? A random, remember, the bacteria wouldn't even know that it's aiming for John Evans. And remember, it's a random, undirected process. What are the chances of having a more complex, higher functioning organism by a random, undirected process? Friends, God loved us so much. He gave us so much evidence. He gave us so much information. It screams, it shouts at you. The evidence is everywhere. Right? So the two verses I want to leave you with, the ones we talked about. First of all, think about the video, Genesis 1:1. In the beginning, God created the heavens and the earth. And I want you to think about that creation. Just think about that, if you would, please. And then, and we'll spend more time next week talking about this, things being created after its kind, and how exactly that's accomplished, all right? And I'll have more show and tell for you next week. Anybody have a closing thought or comment? Looks like we have about 30 seconds remaining here. All right? Pretty good stuff. Yeah. So next week, we're going to cover Babylon, the prophecies about Babylon. You know, and I don't know if I just saw the prophecy on Egypt where God said, I'm going to make you a weak nation and a deserty nation. That may not convince me that the Bible is God's word. Then I look at Assyria and God said, no, I'm going to totally wipe you out. And I'm going to do it by fire and water. And if I saw that, I still might not be completely convinced that the Bible is God's word, but I would be interested. When I get to Babylon, after about the third one of these prophecies, I think I would begin to believe. Right? So God doesn't leave us to guess. He loves us, and He wants to give us the information so that we, in turn, can teach others. We can obey Him, and we can teach others. Right? Any thought or comment this morning? Oh, how good y'all are. Huh? Yeah. Yeah, it's really amazing, isn't it? Yeah. And so next week we'll cover my DNA a little bit more here. And here's my double helix. And we'll go back over that protein molecule thing. And we'll talk about Babylon and look at the prophecies regarding Babylon. Okay, I think I'll go ahead and stop right there.